Hello. In this video we're going to introduce yet another kind of discrete random variable, a negative binomial random variable. Consequently, by the end of this video you should be able to explain what kinds of phenomena can be modelled using a negative binomial random variable, and you should be able to explain how the probability mass function for this type of random variable is derived. Before getting on to that, however, let's first briefly review what we have learned about the geometric random variable, because there is a relation between this type of random variable and the negative binomial random variable. In fact, the geometric random variable can be thought of as a negative binomial random variable with a particular set of parameters. The probability mass function for the geometric random variable is given on this slide. This probability mass function gives the probability that the first success in a series of identical Bernoulli trials will be on the kth trials. Furthermore, it is assumed that all these trials are independent. In deriving the probability mass function for the negative binomial random variable, we generalize these results. We are thus interested in the probability mass function for a random variable that measures the number of trials that we will have to perform before we observe exactly R successful trials. The derivation of the probability mass function for this negative binomial random variable is actually rather easy. Suppose that you are looking for the probability mass function for a random variable that measures the number of times that you have to perform trials until you have two successful events. That is to say you are trying to find the probability that you will have k trials before you get R equals 2 successful ones. If you get the second success on the second trial, that is to say if k is equal to 2, then both of your trials must have been successful. The probability of two consecutive identical trials is just p squared, however, and so the probability that x equals 2 in this case is p, the probability of success on a single trial, squared. If we are looking for the probability that k equals 3, then you need to have two successes in 3 trials. There are 3 ways this could have occurred. The failure could have occurred on the second trial, the first trial, or it could have occurred on the final trial. If the failure occurred on the third trial, however, you would have had 2 successes by the second trial. In other words, k would have been equal to 2. The last trial must therefore always be a success. There are thus only 2 valid sequences. The failure can occur on the first or the second trial only. The probability that k is equal to 3 is thus 2 multiplied by the probability of a single failure, 1 minus p, multiplied by the probability of having 2 successes, p squared. Furthermore, and to be totally clear, the factor of 2 in this expression appears because there are 2 possible orders in which the failure and success in the first 2 trials can occur. We can generalize the insight that we got from this simple example into a general result as follows. We first note that the probability of any sequence of k trials that involves R successes is equal to p to the R multiplied by 1 minus p to the power k minus R, because each of the trials are independent. We next note that the rth success must occur on the kth trial because we are looking for the probability that it takes exactly k trials for us to observe R successes. If the rth success had occurred on any earlier trial, we would have achieved the R successes that are required in fewer than k trials. Having said that, however, the R-1 successes and the k-R failures in the preceding k-1 trials can occur in any order. For instance, the successes and failures can occur in the order shown here, or they can occur in this different order, or even this different order. We thus need to compute how many ways there are of arranging r-1 successes in k-1 trials. In other words, we have k-1 objects in total, r-1 of these objects are of one type, and the remaining k-r of them are of a second different type. We know how to compute the number of ways there are of ordering k-1 objects of two different types, however. We simply use the binomial coefficient that was introduced when we learnt about the binomial random variable. The number of arrangements is thus k-1 choose r-1. The final probability mass function for the negative binomial random variable is thus given by the expression shown here. To be clear, this probability is the probability that the rth successful trial will occur during the kth attempted trial. To conclude, then, let's briefly return to the learning outcomes for this video. I said at the start that by the end of this video you would know what types of phenomenon can be modelled using a negative binomial random variable. As we have seen, if the probability mass function for the negative binomial random variable is evaluated at k, we obtain the probability that the rth successful trial will occur on the kth trial performed. We have seen that all the trials must be independent in order for this result to hold, and we have explained how the expression shown on this slide is derived based on this description and these assumptions. Hopefully this is now all reasonably clear. If it is not though, try working through the video again and seeing if you can understand it better on a second run through. Thank you for your attention.